Hello, a very warm welcome to everyone. I, Arunika Saxena, a master student under the guidance of Dr. Shirly Avargil, is presenting my research in front of you. The topic of my research is chemistry teachers' perceptions of model and students' conceptual model in the context of air quality learning unit. This research is funded by National Science Foundation and conducted at the University of Maine, US. In this slide, I am giving you a brief introduction of the Academic Content Standards, a framework for K-12 science education and the next generation of science standards. Both of these documents are developed by National Research Council. The framework identifies major scientific concepts and practices which are essential for each and every student until the completion of high school for learning science. Some of the important practices mentioned in the framework are developing and using models, scientific inquiry, and engineering designs. This research was conducted in a state that adopted framework and next generation of science standard. My research is focused on the practice of developing and using scientific models. A framework for K-12 science education emphasis on the representation of phenomena through constructing diagrams, pictures, models, analogy, and so on, using different types of modeling tools to explain a specific phenomenon, refining of a model for improving its quality and explanatory power, running a simulation through simple simulating tool for studying salient features of a system that are not visible to unaided eyes, for example, atomic structure, molecular bonding, and so on. What is an authentic scientific model? An authentic scientific model is a simplified abstract representation of a system that highlights its central features explicitly. It is an essential part of a chemistry curriculum without which we cannot imagine of teaching and learning of chemistry. It enables students to generate prediction and help in explaining natural phenomena like evaporation and condensation. It starts with producing an initial mental model in students and eventually develop into a conceptual model by a student. The practice of developing and using scientific models in terms of learning processes tells that models engage students in argumentation and scientific discussion through evidences. Models promote reflection on and clarification of existing ideas. Models used for testing ideas and processes. They also help in obtaining, evaluating, and communicating information. The practice of developing and using scientific model in terms of teaching processes tells that models are strong pedagogical tools. Models can also be used in learning progression to improve the scientific ideas in students. Models can also used in accomplishing educational goals such as conceptual understanding of a particular phenomenon. Why chemistry teachers teach with models? Chemistry teachers teach with models because learning progression through models inform teacher about students' learning. Model assess student knowledge within a variety of representational level of chemistry understanding, for example, macroscopic, microscopic, process, and symbolic. Models give insight into the way a teacher teaches chemistry into the classroom. Teachers can also develop an interest of learning chemistry in students in the similar way used by scientists to develop their models. Teachers can update students' knowledge through the iteration process of models. Why students should use scientific model and how their conceptual understanding affected by models. The practice of developing and using model leads to positive effect on students' attitude toward science and problem solving abilities. These practices also refine student understanding of confusing and challenging topics of chemistry, for example, redox reaction, mole concepts, and so forth. In this slide, I am presenting my research questions. In the presentation today, I will focus on my research question number 1 and some results from the research question number 2. My research questions are as follows. First, what are the teachers' perception of scientific practice developing and using models and how they differ from the way it is described in a framework for K-12 science education? Second, what are the characteristics of students' understanding of models and modeling in the context of PBIS Air Quality Learning Unit? Third, does and in what ways students' understanding of models and modeling associated with their teachers' perception of this scientific practice? Research setting. This research performed in the context of Project-Based Inquiry Science PBIS Air Quality Learning Unit. This learning unit is especially designed for 8th grade students in United States. This unit is strongly aligned with a framework for K-12 science education as well as the next generation of science standards. This learning unit teaches chemistry in the context of air quality. Some of the topics from the unit are as follows. What substances make up air? What state of matter is air? How can chemical reactions be used to improve air quality in your surrounding? This learning unit emphasizes on scientific inquiry as well as on the developing and using scientific models. In my research, teachers as well as students both participated. 17 middle school teachers participated in the research. Out of them, 8 teachers were interviewed from 5 different public schools of Northeast region of US. On the other hand, 450 8th grade middle school students also participated in the research. They belong to 10 different public schools of Northeast region of US. Teaching and learning took place in the context of PBIS Air Quality Learning Unit. Purposeful sampling is used for the selection of teachers and students in the research. In this slide, I am presenting teachers' demographies. From the pie chart, we can see that 40% of the teachers are holding MA degree and 60% of the teachers are holding BA degree. From the graph, we can see that maximum teachers having high level of teaching experience come in the range of 21 to 30 years. Now I am showing research tools regarding teachers in this slide. Research tools used in my research regarding teachers are semi-structured interviews. The questions are based on the perceptions regarding developing and using models. Some of the examples of the questions are: what does it mean to teach with models? How do you use models in your classroom? Did you have a chance to think about models when you teach chemistry? Give examples. In what ways do models help students to think about chemistry? In this slide, I am presenting research tools regarding students. Pre and post questionnaires were given before and after learning the PBIS Air Quality Learning Unit. The questionnaires are model-based and selected from the American Association for the Advancement of Science project, which is related with the drawings and explaining a conceptual model of a chemical phenomena. Some of the closed-ended and open-ended questions from the questionnaires are given in the next slide. In this slide, I am giving an example of closed-ended question. A student draws a diagram that shows how he thinks water evaporates from a wet washcloth sealed in a plastic bag. Based on the drawing, he predicts that if the wet washcloth is left sealed in the plastic bag for several hours, water will evaporate from the washcloth and it will dry out. When he tries this experiment with a real washcloth, it turns out that this prediction was incorrect and the washcloth is still wet. What should he do with his drawing? Note, question 1 also asks the explanation of the option chosen in the post questionnaire. Options given below are A. The drawing should be discarded and not used anymore to make predictions. B. The drawing should be changed so that it better represents what was actually observed with the real washcloth. C. The drawing should not be changed. And D. The drawing should be used to make other predictions until one of the predictions turn out to be correct. Here, I am giving you some time to think about the correct answer of the question. Yes, you are right. The correct answer is B. The drawing should be changed so that it better represents what was actually observed with the real washcloth. Here in this slide, I am giving you some more examples of closed-ended questions. I am giving you some time to get an impression of these questions. Later, I will tell you the answers of these questions. Now I am going to give you the answers of these questions. For question number 2, the correct answer is A. For question number 3, the correct answer is A. And for question number 4, the correct answer is C. In this slide, I am presenting an example of closed-ended question. In a cup of liquid water, when put, the water molecules stop moving. The correct answer here is D. The molecules would not stop moving in the cup of liquid water. In this slide, I am giving you an example of open-ended question. You drink all the water from a plastic bottle, you put the cap on the bottle and tighten it, then you put the bottle in the refrigerator. An hour later, you notice that bottle is dented. Please draw what happened inside the bottle and then use your drawing to explain why bottles dented after being cooled in the refrigerator. In this slide, drawings of two different students are given. In figure 1, in the bottle first, a student is trying to explain that molecules are further apart at the room temperature. In the same bottle, after being cooled, a student is trying to show that molecules come together make the bottle dented. In this slide, students are trying to represent their conceptual understanding of the model regarding the phenomena from the topic properties of gas. In this slide, I'm presenting my research method. My research is a mixed method approach. In qualitative data interviews and two open-ended questions were analyzed by directed qualitative content approach. Categories were identified from a framework for K-12 science education. These categories later cross-checked by inter-rater agreement. On the other hand, quantitative data, pre and post closed-ended questionnaire were analyzed to assess the students' conceptual understanding. We graded as correct and incorrect responses to these five closed-ended questions. Then after we applied descriptive and inferential statistics. Now I am showing finding from my research regarding teachers' perception of model. From the teachers' interviews, we analyzed 179 quotations and 7 categories. Category 1, characteristics of model, is at its highest, that is 20.1%, and category 7, used to assess learning, is at its lowest, that is 6.7%. In this slide, I am showing results from teachers' perception of model. For example, in the category 4, students' ability to develop models, which describes successes and challenges faced by a student while developing model in the classroom. One teacher said, having them develop their own model to models think you can't see or touch in some cases is kind of difficult. Things are so abstract that I think it's hard for them to model. Taking another example from teachers' perception of model, in the category 7, used to assess learning, which describes assessing students' knowledge through models and identifying their misconceptions, a teacher said, I ask a student to create or explain models quite frequently as an assessment for their understanding. In this slide, you can see different examples of categories: positive conceptualization, negative conceptualization, as well as suggestions from different teachers. For example, in the category 4, students' ability to develop model, positive conceptualization show the process of developing models and hence students' conceptual understanding. But on the other hand, negative conceptualization show the abstract nature of chemistry make it challenging for a student to develop their own models. A teacher suggested in this category that we should use different type of models in teaching and learning chemistry. Taking another example from the category number 7, used to assess learning, positive conceptualization show models are good as an assessment tool, but negative conceptualization show models do not provide sense as much once they get dispersed or dismantled. But on the other hand, one teacher suggested that we should make students feel comfortable with their drawings and should not grade them on the basis of art. In this slide, I am showing you the findings regarding teachers' perceptions of developing and using models. From the graph, you can see that most of the categories are positively conceptualized. It means that the categories are aligned with the framework. In this slide, I am showing my finding regarding teachers' perceptions by category. We find two important findings from this graph. The first finding is related with the category using a variety of model. We can see there is no negative conceptualization in this bar. That means all teachers agreed with using a variety of models while teaching and learning chemistry in the classroom through models. Another finding is related with the category used to assess learning. Very few quotations from the teacher's interview were analyzed, which is related to the models as assessment tool. But when teachers relate the category to models as an assessment tool, they are very positive. But in actuals, teacher did not able to conceptualize model as an assessment tool. This is an important finding. Now I'm showing my findings from students' conceptual understanding and modeling skill. In the graph, you can see significant differences in the question number 1, 2, and 4. Question number 2 and 4 showing increase in the graph. On the other hand, question number 1 showed the decrease in the graph in post-questionnaire test. Question number 2 and question number 4 are easy with respect to conceptual understanding of a student. We can also see that in question number 5 there is no significant difference in pre and post test. In my next slide, I'm going to explain you the reason behind the decrease in question number 1 and no change in the pre and post questionnaire responses of the question number 5, because these questions are difficult and with respect to conceptual understanding of a student. In this slide, I'm going to show you the finding related with the success rate of responses in question number 1 by all the students. In this graph, I'm going to relate question number 1 and explain you the decrease of the graph. One possible explanation is that a student had to choose their answer for explaining and thus thought of an option which will be easy for them to explain. Thus, they choose D. The drawing should be used to make other prediction until one of the predictions turn to be correct. It seems that students do not understand that once they draw something, they need to change it to represent what actually happened with the real washcloth. In this slide, I'm showing you my findings regarding the success rate of responses in question 5 by all the students. We can see in the graph that there is no significant difference in the pre and post questionnaire test of question number 5. It is because this question is very complex for the student in terms of their conceptual understanding. Students do not change their perceptions from pre-test to post-test. It seems that they did not perceive model as something that a student need to revise and change. In this slide, I am showing examples of explanations from open-ended question 1 by 2 students. One student who chose option B explained, if the washcloth is in a bag, no air can go into or out of the bag, making the washcloth stay wet. Another student who chose option D explained that he should keep it because it will help him with other prediction. We can easily understand that why students choose option D so frequently in question number 1, because it is easy for them to explain. In this slide, I am summarizing my finding regarding teachers' perceptions of model. Teachers perceive the practice of developing and using model as extending students' thinking about a phenomenon. It's challenging because every student has their own perspective about the model and might understand and interpret it differently and accordingly, making students bored and aloof when they have to go back to the same drawing for the revision. It is necessary to be revise the model to develop understanding of the model. Teachers relate this practice of developing and using model as an assessment tool at its least. In this slide, I am summarizing finding regarding students' conceptual understanding and modeling skill. Teaching with air quality unit improved students' conceptual understanding and understanding of models in question number 2 and 4 in post questionnaire as compared to the pre questionnaire. Students choose easy option in closed-ended question number 1 because they were asked to explain the reason in their words for their choice. In closed-ended question 5, there is no significant difference in the responses of a student of pre and post questionnaire test, as the level of question seems very difficult for the 8th grade students. Our research aligned with the updated literature regarding the practice of developing and using model and emphasizes that construction and refinement of model encourage students to think deeply and imaginatively about scientific ideas. In the recent research, it was shown that revision of the model is an important factor in learning chemistry as it reconstructs the understanding of the phenomena in students. Teachers' perceptions of model as a tool for evaluation and assessment in learning chemistry progression is low, but their understanding is very high. In another research that shows models and modeling practices are very good instructional aid for teachers to monitor their students' progress. Continuing discussion from the previous slide, our research aligned with updated literature regarding models emphasizes that learning abstract phenomena of chemistry through models strengthened the conceptual understanding in students. As we can see this that in post questionnaires, students' responses increase in question number 2, 3, and 4. In the recent research, it was shown that models as a tool help students to perceive conceptual understanding. We can also see from the question number 1 and question number 5 that developing and using models make students' thinking visible and give teachers an insight into the current understanding and alternative ideas of students. Another study showed that models have a great effect on promoting students' views, especially in learning and abstract phenomena. Our research also have some limitations. First, relatively very short time had been given to the teachers to teach PBIS air quality unit. Second, very specific population participated in the research with a very small diversity. Our research show theoretical as well as practical contribution. Theoretical contributions show a comparison of the teacher's perception of developing and using model with the recent standard of framework for K-12 science education is unique. The comparison filled the gap between what teacher thinks about the model and how it is conceptualized in the framework. The research is distinctive in trying to connect teachers' perception of developing and using model with the students' conceptual understanding. Practical contributions show designing professional development program for teachers aiming at the practice of developing and using model as it is conceptualized in the framework. In our research, most of the teachers and some categories are aligned with the framework, but there are still some work to do in the future. For example, some teachers did not conceptualize models as an assessment tool. So we recommend to examine perceptions of teacher with other practices in a framework for K-12 science education and their alignment with teachers' perception. Foremost, I would like to express my sincere gratitude to my advisor, Dr. Shirly Avargil, for her contribution in my master's study and research, for her patience, motivation, enthusiasm, and immense knowledge. I would also like to give thanks to my chemistry education research group, especially to Dr. Gabby Schwartz and Yoram Zemil. We want to thank also to Professor Mitchell Bruce and François Amir from University of Maine for their advices and support in this research. And also thanks to all the listeners.